a startup company developing a 3D streaming technology similar to Google Earth. He was also responsible in the Safran Group for organizing new collaborative processes in the domain of mobile telephony. So before being a manager of RIT Paris, he was also a CTO of Cantoche, a company developing avatars and virtual assistants. He's led or contributed to several French and European collaborative research projects. So please give him a warm applause. Thank you.
Thank you. So it's great to speak after the talk of Mary, because I will try to explain very difficult things which are related to the fundamental differences between the brain and artificial intelligence. So we have now at Rakuten Institute of Technology, we work on many projects using deep learning or any other machine learning techniques. But I started to work with neural networks in the 90s, a very long time ago. And so at that time already there were many projects with neural networks, not the same technique than now, but also the old export system. So I want to say a few words about the evolution of artificial intelligence in then and where we are now and what we can expect in the future. But not from a very technical viewpoint, more in between technical and philosophical viewpoints. This is a slide I already showed last year at this same conference in 2015. And at that time I said that we were close to have a computer win at the Go game, and that Facebook would probably succeed in that, but it was actually Google DeepMind who did this year, and the AlphaGo computer game program succeeded in beating a great Go champion this year. And we also see the self-driving cars arriving, of course, and I didn't mention the previous one, everybody knows about that. And the big trend now is about chatbots. Let's see that. So first, a few words about this victory of AlphaGo against Lee Sedol. There were very amazing, very unexpected move by the computer. And this is an example of those. Move number 37 on match 2, and the audience was amazed, and we heard many funny comments, and people thought it was a mistake by somebody, and after a while they understood that it was a very good move, because no one would have played there, no human player would have played them, because they would have played lower, because it is pretty high. I'm not an expert, but roughly it's too much in the center, and that's too risky. And what's very interesting is that afterward, this kind of innovation made the greatest champion progress, because they think about new ways of playing. I won't go into the technical detail of the AlphaGo, this is another story, but it's mostly about deep learning and reinforcement learning. So it seems that one after the other, a computer will outperform the most skilled humans. As soon as the task is well specified in a restricted domain, at some point a computer program outperforms the most skilled human. We can't be sure of that, but this seems to be the case every time in any case. Something very difficult, which is not well achieved by computer for the moment, is really understanding natural language. Anyway, we see that a lot of chatbots are coming. Many people think it's a new kind of user interface that will replace almost everything. So we're quite high in the hype cycle. You know, the hype cycle when you have a lot of expectation and then it lowers and it goes to a more productivity level. So we're quite high, I think. But it's very interesting that there are so many chatbots arriving. And at the same time, everybody kind of agree that computers don't really understand the natural language. They can do a lot of things like translating and many things, but really actually understand language is not what they do well. And I will, in the next slide, I will try to explain what understanding can mean. Maybe you know that one of the first chatbots was developed 50 years ago. It was called Elisa. It was faking a psychologist. And probably you know about the Turing test. Turing test means that when a computer passes the Turing test, it means it can fool a human in thinking that it was a human he was discussing with. And this ELISA program succeeded in passing the Turing test for many people. Many people thought it was like a human. This was 50 years ago. Now, the biggest internet companies are working on chatbot, or have all the standard lists of Google, Facebook, and so on. So we can think we made great progress in them, but actually what do we have now? So we have mostly, and I come from a company creating virtual assistants, so I knew about the history of that a little bit, and we have still now, most chatbots use predefined questions and answers. We have a big database of questions and answers, and it's very manual, but there is much more intelligence now in the way you can match a query with something you prepared in the scripted dialogue. So there is where things have progressed. Or you have much more automatic generation of language with techniques similar to what is currently used in translation, which is about matching sentences in one language to sentences in another language. But in this particular case, you match questions with answer. So you automatically, but really fully automatically generate answers by training a program, training an algorithm, and feeding it with a lot of existing dialogue, and then it knows how to generate answers corresponding to a question. The problem is, it does not know what it talks about. There is absolutely no meaning attached to it. So here an example you can read. It's from a paper from someone from Google, quite recent. So it's really impressive how some text can be generated, how real it looks like, but you cannot use that to do technical support because it's anything. So to summarize, we have these two cases, things like mostly similar to good old-fashioned artificial intelligence, like export systems, things very manual, and it's easy to attach some symbolic information, some meaning to it because it's mostly manual, even if there is, as I said, a lot of intelligence in matching natural language queries with some topics. Or you have data-driven dialogues, which are so powerful, it's really impressive, but it's very difficult still now to combine them with some semantics. So I use the word semantics. It can mean many things, so I will spend some time talking about semantics. At Rakuten Institute of Technology, we work on different projects trying to extract some semantic from raw data. So Ankur explained very well in a previous talk about what is unstructured and structured data. So this is what we do. So from a raw image or text, we try to extract some semantics. But what is this kind of semantics? Well, it's just that we try to compute semantic distances between objects. So it's mostly data-driven semantics. So we are able to gather different objects, which are pictures or text, and say that they represent some close objects that are a close meaning, or close that are similar in their symbolic information. So this is very powerful. But so you're able to create clusters of product, but then you're not able to say what they are. So you have to manually tag them. This is very useful, but the computer itself knows nothing about what they are. It's just capable of gathering different, because the principle is to convert this text or images into vectors in some appropriate space where some kind of distance is meaningful, related to the categories of the object, for instance. This project was already mentioned several times today. So this is another thing we do where we try to extract semantic from images. So this is the semantic is in this particular case is the category of the object. So now, if we imagine that most people think about now we will go through, we're going toward the singularity point where we have super intelligent computer. Let's assume we will have very intelligent computer in a few years. Then we will have to assign some goals. We'll have to tell them to do some things which will be kind of high-level goals, otherwise it's not useful to have intelligent computers. So we will tell them like, make this economic mechanism work better, make those people happy. That would be great because we can assign very high-level goals. But how will we know that the computer understands that? It's quite impossible, it's a very big problem. So it's, again, a problem related to the meaning and the semantics. So one theory explains things in a very simple way. This is the computational theory mind. So the brain is a little bit like the hardware, and the mind is a little bit like the software. That makes sense. That's so simple. So then all the problems disappear because it's exactly the same. Our brain is just like a computer, and the meaning we can attach to things, this is the same meaning the computer will attach to things. This is one theory. And there is an opposite theory which is much more interesting. It's a bit more complicated also. So one paper was written by John Searle, who is very famous, and his Chinese room argument is also very famous, but I will briefly explain about it. So the idea is to make you think about what meaning is. This is very difficult. This is why he invented this thought experiment, like Einstein did with he imagined chasing a light beam. Thought experiments are very useful. So this thought experiment is that you imagine there is someone in a room, locked in a room. This is a Chinese room, and he has to receive questions in Chinese, and he sends answer in Chinese. The questions and the answers are on pieces of papers, and he has a very big book that tells him how to match the answer with the question. It's really a very good book, and it takes a lot of time, but that works. So the guy is able to talk in Chinese. So he passes the Turing test. He's not a computer, but actually it's like a computer because the pieces of paper are like a database. The book is like a computer program, and the guy is like a computer. There's no difference in this case. So he passes the Turing test, though he doesn't understand a single word of what he says. So now imagine inside of this guy we have the computer, or instead of this guy we have a human, not understanding Chinese, or you have another person understanding Chinese. So what's the difference between this guy understanding Chinese and the two other cases? Maybe you understand through this thought experiment what meaning is and what semantics can be. So now I will take a few points in both theories. So according to John Searle, and I encourage you, I recommend that you have a look at a few of his talks. Computer intelligence is observer relative. What does that mean? It means that if you ask the computer to do 1 + 1 = 2, 1 + 1 is just something you give as an input, and 2 is something you receive as an output. But it's your interpretation that this is 1, 1, 2, and equal. Computer knows nothing about that. So computation is a fact of interpretation, and computers are purely syntactical. There are absolutely no semantics inside, except in the sense that I mentioned before related to machine learning, which is very not the same. So simulation is not replication. What happens in the computer is that we simulate some feature of our brain or some other things, but we don't replicate what is inside our brain. And for Ray Kurzweil, which is very famous also, a promoter of the singularity, brain mechanisms are replicable. It's exactly the same as what happens in computers now. And so computers could be conscious just like humans, why not? So one day you will be able to upload or download your mind from a computer, so you will become immortal. Think about the previous talk now. So what's next? So probably there is no limit in artificial intelligence capabilities to solve many problems as long as they reside in a restricted domain. But what we call strong AI is not at all on the horizon. People say in 2030 or 45 we will reach this singularity point with superintelligence. It's not on the horizon. And even there is fundamental differences between computer and human brain. This is John's viewpoint, and I'm quoting, minds are semantical and computers are syntactical. And that's it.
So do we have anyone in the audience with any questions?
It's very interesting to consider what is artificial intelligence, and we can talk all day about this, but what if you had a very simple mechanism that didn't even look like a computer? Say it was a system of ropes and pulleys and weights, and somehow you could program this large machine to answer a question in a fashion that seems to you to be artificially intelligent. So you have this large contraption, maybe it looks like a machine that can do weaving or production, or it looks like a factory robot perhaps, or even something more primitive with ropes and pulleys, like I said before. And you can program it to answer a question like, why is the sky blue? And it gives you a satisfactory answer, something that you might have heard from a physicist or an environmentalist or something like that. Even though when you look at this machine, it just looks like ropes and pulleys and something that's not impressive at all. And yet it gives you an impressive answer that might have come from a human scientist. Wouldn't you say that that machine is now intelligent?
Well, what you describe is exactly what a computer is. There is absolutely no difference. A computer is meant, there is some hardware. So in your case, the hardware are different things, but it's exactly the same. Yeah, the difference between a computer and our brain is that there is some separation between what is at the material hardware level and what runs on it. So you can understand precisely where it starts from like bits or even qubits or anything. So it's totally different. And you're right. If a computer or any machine passes the Turing test, by definition, it means you cannot distinguish between what it does and what you do. But what I try to explain, which is the viewpoint of John Searle, is that there is a fundamental difference that you can feel when you're thinking.
But that's irrelevant.
Is it relevant?
It's not relevant, because you get a satisfactory answer anyway. So if the answer comes from a cardboard box with a mechanism inside, or a human scientist, it's still a valid answer. So you should say it is artificially intelligent.
Yeah. It's very useful, and it's very good that we can get these answers. But what I wanted to explain is what still in this case, what would be the difference between what we do with our brain and what this computer does. But yeah, this is the same. This would be the same feature.
Thank you very much again. I believe the time is up. I think that potentially there are people who want to continue the conversation, perhaps then outside. Thank you again, and please give a warm applause to Laurent.
The human brain has some kind of magical quality that the human brain